So okay, let's continue our lecture, and I will continue with the local structure of crystalline phase change materials. So just let's go back for a few minutes to the crystallization, to the phase transition in the GST system. So if you measure sheet resistance against the heating temperature, and if you start with amorphous phase, we heat up it to the specific transition temperature, like 160 centigrade, and then they have the transition from amorphous to the metastable, so-called metastable crystalline phase, which has one value of resistance, and then we can see also that this resistance is gradually changing ferro. So here you can see one resistance, and this is another low resistance state. And then we can also transition to the so-called stable crystalline GST 225 phase. So it seems to me that in this system we have different type of crystalline phases. Here, which has in these phases they have different resistance. Now let us look to the crystal structure of the first metastable phase. It was studied by different groups, by different methods, by X-ray diffraction, by TM, and by theory. The problem in this system here that you can produce this stable phase, so-called trigonal phase, as a powder, as a crystal, really large crystals, by putting all components and then heating up, then quenching, then you get all this stable phase, a single crystal, and you can study the crystal structure of this phase. But this phase is not so interesting for phase change application because it does not involve in the phase transition between amorphous and metastable phases. But it's as I showed before, it's very interesting for the thermoelectric applications, or in the case of the phase change superlattices. But these phases, metastable phases, or here cubic phases, it's difficult to produce, or it's almost not possible to produce as powder. The first results they were produced like the group from Japan. They deposited film films, then crystallized them, then scratched the whole film film from the substrate, and crystallized, deposited, crystallized, and again, and so they get some amount of powder to start for studying of crystal structure, and they derived the average structure of these materials, and it belongs to the cubic to an NSL, that type of structure. So here we have ordered tellurium sublattice and disordered germanium antimony sublattice, so-called cation sublattice. And on this cation sublattice we have around 20% of vacancies. Some HRTM data as well as theory, they also supposed the formation of highly ordered phase where the vacancies are ordered in the layers. However, in X-ray diffraction they claimed a random distribution of vacancies. We also looked to the structure of laser crystalline spin film, and we found that this, on the average, this is also cubic structure. It's also, let's say, layered structure, like the sequence of layers ABC. So cubic. This is the tellurium sublattice, and this is the germanium antimony sublattice. And what we see that this sublattice it does not show too much variation in the contrast. So it seems to be the vacancies which are here, these sublattices, they are randomly distributed. Also, this germanium antimony and vacancies, they are off-centered, located in the octahedron. So this is the main structural unit of this phase. This is octahedron. As you can make it here. It's in 2D. If you like draw here, Then this is octahedron, and this is the central atom germanium antimony vacancies. There's, let's say, like the off-centered location. This off-centered location of these atoms brings to the so-called pulse distortion in this system. So what does it mean, pulse distortions? It means that they have different distances between the atom, longer and shorter distances. And this brings the system to so-called pulse, this distorted system. But as I said, there is no moderate of vacancies in this system. So maybe we found that the crystal structure of this phase, this is important in the phase change for electronic optical memory. So this is most probably this is phase with low resistant one, and this is so-called, let's say, metastable phase. But let us look, can we produce such a phases here? Can we found maybe another structures, and maybe can we see moderate of vacancies into the layers? Yes, it's possible if you simply take the thin film and if you heat it up to the temperature 200 centigrade, like here, you see this state, it has different resistance state. And so it has also different crystal structure. Now here the vacancies, which were randomly distributed, they start to form so-called vacancy layers. Here these dark lines in this image, these are really vacancies which are ordered into the layers. So the vacancies which were randomly distributed on cations of that is they moved to the neighbor, since we have 20% of space there, and then they formed empty spaces, and this is vacancy layers. This is high resolution image. This is the larger area. And this is A15. Fast Fourier transform image. This is mathematically calculated image from this large area. And what we see here, that between the main reflections, we see also additional spots here, 1, 2, 3, 4, 5, 1, 2, 3, 4. And this means that we have really ordered of vacancies layers. And because this is 2 to 5 composition, we have building blocks in this phase, which consist of 5 tellurium, 4 or 5 tellurium layers. So in this case, this example shows 1, 2, 3, 4, but here 1, 2, 3, 4. Okay, so some building blocks with 5 tellurium layers. This is 5, here 4, and so this is the new structure, the ordered vacancy layers. Also such ordered structure, the vacancies layers can be also produced by thin film growth. If you take, for example, PLD, use pulse laser deposition, and if you deposit these materials, again at the temperature like 220 centigrades, it's a little bit higher than in this case, but it's still less than the transition temperature to the stable trigonal phase. This is like around 280 centigrade. Then we also obtained highly ordered vacancy phase. Here, this peak shows the superstructure. This belongs to this, shows the ordering of vacancy layers. Also, high angular dark field image, it shows also the formation of highly ordered vacancies in this system. Also, 50 shows nicely here 1, 2, 3, 4. 1, 2, 3, 4. Yeah. So 4 means 5 layers in the field. So from that we can also study the local structure of this vacancy ordered phase. If you have this highly ordered vacancy phase, we can derive the unit cell. Here we derive from epitaxial thin film. So this structure belongs to the trigonal structure. This space group and the unit cells parameters, it's a little bit larger compared to the cubic phase, so especially C. What we have here, we have ordering of vacancies into the layers. Here the dark lines. The stacking of the layers here is ABC, 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 so it remains cubic. And crystallographically, this structure is similar to this compound, germanium antimony telluride, with 6 tellurium layers, and this shows like a superstructure of rock salt type, the ABC stacking. Here what we have that the formation of the antimony-rich layers close to the vacancy layers, and formation of germanium-rich layers inside of such building units. So the next phase transition occurs at a little bit higher temperature, like 300 centigrade, 280 centigrades, and then we have here the transition from this vacancy ordered phase to the stable trigonal phase. They structurally they are similarly very similar in the sense of building blocks. So in the structure of building units here. So here we have also antimony-rich layers which close to the so-called van der Waals gaps in this phase. But these are not really van der Waals gaps, as you know from the graphene, for example, or graphite. So you have here the distances are smaller, and they represent also like vacancy layers. But to distinguish between these two phases, we will call them van der Waals-like gaps. Also, the difference between these two phases that the stacking across the van der Waals gaps, it changes from the cubic to the hexagonal. So we have here ABC, AB, AB. So now we change ABC, ABC, AB again. So it's a hexagonal. And this structure now represents really trigonal, belongs really to the trigonal system. And again, this system, the main unit motif, this is octahedron, as it contains of an octahedron. And here we have also germanium antimony, which are off-center located. But here the cation sublattice is now more ordered. So there is no vacancies on this sublattice. Also, the density of this phase is a little bit larger. Here you see 6.4 compared to I think for cubic it's 6.2. So there is slightly differences, but not too much. So now, so the local structure, as I said, that consists similar to the vacancy ordered phase. There we have layers close to the van der Waals-like gaps. They are antimony-rich, and inside of the box they are germanium-rich. Here also this phase was studied for many years, and here there was proposed several different sequences for these phases, how this stacking can be formed here. One of the first models, for example, for Coyer, proposed based on TM. He proposed the antimony, pure antimony close to the van der Waals-like gaps. Petrov proposed germanium. Matsunaga, he proposed germanium mixed layers consisting of germanium antimony, and the single diffraction data. It shows also the formation of mixed layers, germanium antimony here, but the difference in the occupancy of germanium and antimony on the cation sublattice. We also did some experimental work on this space using TM. Did some experimental and we simulated also the intensities of this data, and found if you use urban model, it fits much better to our experimental data. And this shows that here the layers, cation layers, they are also mixed layers, so there is no pure layers in in this structure. So all structures are highly disordered on cation sublattice, and they are highly distorted. Also, there are different similar phases in this system. I don't want to consider cubic phase. I will also only consider the trigonal phases, the composition like germanium 1, antimony 2, tellurium 4, and germanium 2, antimony 3, tellurium 6. They are also similar in the composition and also in the structure. Like for trigonal phase, it's also they consist of highly disordered cation layers, and they are highly distorted system and consist of highly periodic vacancy layers or van der Waals like gaps. The only differences in these phases between all phases of the taken and the unit cell. So for 3 to 6, it has a huge unit cell. This is C-axis, so the huge C-axis here it has 33 layers per unit cell. 1 to 4 it has 21 layers per unit cell, and 2 to 5 it has only 9 layers per unit cell. The differences in this system is only in the average concentration of vacancies on cation sublattice. If we talk about cubic structure, so we can estimate this the number of vacancies by using this basic relation. This is number of vacancies equal to 1 minus 6 divided by 3 minus 2, 6. And x for here, if you look to the composition, like if we can write a germanium tellurium x, antimony 2, tellurium 3, 1 minus 6, and if we take x1 equal to 1, when we get the pure germanium telluride, and we can see that it has, according to this equation, should have no vacancies, like 0%. Some reports gives the value up to 10%. So maybe there are some vacancies in this system. If they take the value x equal to 0.0, then they get the phase GST1 to 4, and it contains 25% of vacancies. Now, if you increase the amount of germanium and antimony, then we get the phase, our phase GST2 to 5, and it has 20% of vacancies. And for antimony telluride, the low germanium, it has like the number of vacancies. It's on the average of 33. So now let's look how to produce these old structures. As I said, one approach is to use thermal heating. You can start with amorphous phase and heat up the thin film and go through the different transitions. But for some application, maybe you need a highly ordered structure and single crystallized structure, and then you will use the thin film growth technique. One is like VLD, pulse laser deposition, and by using this technique you can control the structure of your thin films by different parameters. Shirender will consider this in the tutorial, but I will show a little bit on this. So depending on the substrate, so we glue the thin films as epitaxial thin films, and for epitaxial thin films you need to heat up your substrate to a particular temperature. Good for this system for phase change materials that they are crystallizing at very low temperature compared to oxides, for example. Here you have a crystallization like between 180 or epitaxial growth between 180 and 250 on silicon 111 substrate, and depending on the substrate temperature and like laser energy and pressure in the system, background pressure in the system, here in this case argon, you can produce either vacancy ordered phase or van der Waals like bonded phase, or you can produce a mixture of these phases. interestingly, how can these phases be grown on such substrates? So if you think about epitaxy, many materials they are directly attached to the substrate. In the case of phase change materials or in these layered structures, what happened if you grow, then during the growth, the tellurium passivation layer is formed on the substrate. This is self-organized process. So we did not want to grow this layer, but after the growing it and study the system, we found the formation of such a tellurium-rich layer, and then after that we have here no space. So this is like gap, van der Waals like gap, and then our structure thin film is growing further on that. And this is also like vacancy or van der Waals like gaps. So here we have like van der Waals like quasi van der Waals like epitaxy of phase change materials. Then also one structural feature of these thin films that they form like rotational in-plane domains. Here in the pole figure measurements you can see. So you have in your system, if you would have one domain system, you would see the image like this, highly oriented, all atoms in the zone X. But if you have a domain, it's a little bit rotated, and then this nice atomic structure, atomic columns, they are disappearing. You see only the lines coming from tellurium and maybe here from germanium, antimony. So we have a little bit slightly rotated domains, and here we found these are up to 6 degrees. Here it's up to 6 degrees, and this is somehow also self-organized process, and maybe also because maybe of strain relaxation induced by strain relaxation, because we have here around 10% of misfit between the thin film and substrate. How to relax, how to do this misfit, how to adjust and relax. First, one mechanism is the formation of dislocations. We found it also formation some dislocations between the thin film and layer, but another mechanism is this in-plane rotation. So then the system can be better adjusted to the substrate and reduce the misfit strain. So now some defects, because it's also important to know which type of defects can be formed in the system. One type of defect which we found, and also other group have found, is the so-called like bilayer defects. So how they are formed? Just we will start with composition: germanium 2 antimony 2 tellurium 5. This is this trigonal phase, highly ordered phase, and it has 5 blocks per. Consists of 5 blocks, and then van der Waals caps 5 blocks. 5 tellurium consist of blocks with 5 tellurium layers. So here we have 5 tellurium layers. This is one building block, and then van der Waals cap of vacancy layers, and so on. But sometimes in some places this periodicity with building blocks with 5 tellurium layers is distorted. Here we have 5, 5, 5, and then suddenly it's 4. And so here, or 4 and 6. And at this transition, you see that the height of the building blocks has changed here. This is 5, this is 6. And so to compensate this change in the height, there is a formation of such defects like building, like bilayer defects, like here between 5, 4, 4, 4, 6. And this is also so-called chemical disorder in this system. So in the X-ray diffraction, you can see nicely that you produce GST225, but on the local scale, you see in the microstructure the formation of building blocks with 6 tellurium layers and with 4 tellurium layers. But if you combine them, this will like 6 plus 5, on the average you get 2 blocks with 5 tellurium layers. So this is normal and somehow intrinsic feature of this system. In the case of GST1 to 4, you can grow really nicely thin film with building blocks with 4 tellurium layers, but for GST225 this is intrinsic feature. And then you form here like a bilayer defects. Here you can see maybe better. This is magnified image. Again, the transition between 5 building blocks with 5 tellurium layers and 6 tellurium layers. And this is here the transition area. Here this is van der Waals-like layer, and this is van der Waals-like layer, and this is the transition area. So, but what is this bilayer defects? We can call it, okay, it's changing in the height of the bilayer. We have some strange contrast here between the atoms. So this is the tellurium atoms. It goes into the tellurium layer. It goes into germanium antimony layers, and here also the same on the left side. It's tellurium layer. It goes into the germanium antimony layers. If you just take this defect, extract it as monolayer, and then try to make a structure from that, model structure from that, we found that actually this is like a stacking fold. So if we extract here one layer, and we can see one part of the domain, and this is the next part, we can see that this is the bilayer defects. It's actually the stacking fold. So here. It's also very similar to the gallium nitride. They also form such particular stacking folds. So also interesting in this system that such cation layers close to the van der Waals caps, they are very mobile, and you can reconfigure the system by using the electron beam. This is to the properties of this system. So if you, for example, to expose of these cation lines to the electron beams, we can first the layers to the van der Waals-like gaps. This is empty space. So we moved it here. First it shows the flexibility of the system, but it shows also that we can create this bilayer stacking fold directly in the microscope. Here you see this is initial system, and then this is rotated, so the two layers they are flipped, rotated, and then you see here also such a formation, such a bilayer defect. So, and then the system is also reconfigurable. You can also bring back the system again to the initial state if you here expose your area again to the electron beam. So these defects also bilayer stacking folds, they're also mobile, so they are not static. You can also move them. This may be interesting for mechanical testing, or for discussing on switching mechanism in this system. So here we created this bilayer defects again by exposure of the layers to the electron beam. So we can create this bilayer defect with the length of 2.5 nanometer. And then if they expose the area close to the bilayer defect, we can flip through these layers, cation layers, so we can extend this defect. We can make it larger. So this is to the properties of this defect. Now let me consider the local structure of another phase change material. This is germanium telluride. It contains less vacancies, as you know, but according to this phase diagram, it contains different polymorphic modifications. Like there exists the high temperature cubic phase, beta phase, crystallizing in this FM33 space group. It's stable about 640 K. And there are two low temperature phases, like rhombohedral, alpha germanium telluride, crystallizing in this group. This is binary analogy to the A7 structure. And rhombic gamma germanium telluride with a structure type tin sulfide. So for phase change application, again, we use this rhombohedral phase, alpha phase, and the structure of this alpha phase is crystallized in this space group 160 as R3 and H. Again, this is also belongs to the trigonal crystal system. That is why I call it trigonal. In the literature, you'll find that the author calls these all phases like the hexagonal phase. But you should always look to the crystal system. Some are crystallized in hexagonal, some are in the trigonal. Hexagonal is subsystem of this trigonal system, and you should really look if it's trigonal or hexagonal. So if you look again from the particle along the A-axis, we can see that the germanium tellurium, they make layers here, but there are no vacancies, or this system it stays in this state of during the different temperatures. So there is only amorphous to crystalline phase change and no other transitions. But as I said, some publications they reported 10% of vacancies, and how they found it, they just make a doping of this material up to 10%, and they found that up to 10% there is no crystal change in this system, so they concluded that it could be 10% of vacancies. Maybe, I don't know. So, but it's a cubic system, it's ABC staken, so here we have ABC is taken. Trigonal system, so hexagonal staking here. Now here this thin film, these materials, it can be obtained as a bulk, as powder, a single crystal, but also you can grow this this thin film, these materials as thin film, and here there is so it also started to crystallize at low temperature, relative low temperature. So epitaxy like starting from 200 centigrade, and it grows. You can even reduce the crystallization temperature on this material if you use a buffer layer of antimony telluride. So we deposited antimony telluride, and then we grew germanium telluride, and then we can produce this material starting at a temperature of 150 centigrade. So this is the interesting how you can manage the crystallization temperature in the case of epitaxial growth. One interesting feature in this for germanium telluride, it's trigonal, but it can be also represented as rhombohedral unit cell. So you can make operations, and then you can represent this cell crystallography as rhombohedral with A0.61 and alpha 89.0 degree. And it brings that you can find sometimes in the X-ray diffraction pattern the splitting of 111 or 00 of these reflections. So this is actually C growth, and you have like a splitting of these reflections. And this is because you have here, due to this crystal rhombohedral unit cell, you have a splitting of 111 and -111 oblique planes in germanium telluride, and it brings you to the formation of two peaks. Because sometimes I had this recently discussion with one PhD student, and he asked me why do we have this splitting, and I said, okay, look to our paper, and we discussed it. But there are also papers in 2015, I think, they also observed the same splitting for MBE grown, for molecular big epitaxy grown thin films. So also one interesting feature during the growth of this germanium telluride, this is so-called blackout effect. So if you grow your thin film, you can monitor the growth in situ by using reflected high energy electron diffraction, REED. And in REED, what you see, so you expose your surface, your thin film surface on the small angle, and then you record here the diffraction. So you collect the diffraction. This is like 2D diffraction, and it's like a streaky pattern always. If you start with your substrate, in this case it's silicon, then after 1 minute of growth, something is happening here. You see here like a blackout here, so no streak pattern, nothing. And then after 1.5 minutes, you can see that some streaks are forming here, and here after deposition you see here like as deposited film many streaks. So here there is a formation of like metastable state, maybe amorphous, and then this amorphous phase is crystallized into the crystalline phase. So, but it also has been observed not only by us, it's also observed before in our papers. We don't have this blackout if you use antimony telluride as a seed layer. So after 1 minute you see the really streaky pattern. So there is no blackout. So there is a direct crystallization. And this is maybe due to that somehow germanium telluride grow differently as trigonal phase change material. So we did not study here really the interface, or no, they looked also with TM, the HRTM here, and we did not found this that it forms with like quasi van der Waals epitaxy. So maybe this is the difference here. Also the difference, if you look germanium telluride, it's also considered like 3D bonded material. And the layered structure like germanium like GST225 trigonal, it's like they consider, or antimony telluride, they consider it like a 2D bonded structure. If you grow such a 3D bonded structure, germanium telluride, without buffer layer, we see that the surface of thin film is very rough. So we see here some faceting here, and in AFM you can see the roughness, you can measure the roughness like on the average of 5 nanometers. But if you use these buffer layers of antimony telluride, you can reduce the roughness of your film up to less than 1 nanometer, and you can see it's in the TM images very nicely here, smooth surface and maybe one step here which is less than 1 nanometer. So also there are some defects in this system because of this rhombohedral symmetry, and this is also typical defects in such germanium telluride. They have been also observed in the, I think, in single crystals. So if you consider the TM image here, you can see some interesting contrast. So you have different area, B and D, and if you calculate the E50 pattern, it shows typical E50 for germanium telluride, so no additional reflections. Here you can identify the structure, trigonal space group. But here in between you can find some interesting area which are in HRTM that appears like layer structure. In E50 it also has different pattern, like here you have more reflections, and also if you use this is HRTM, it's a phase contrast image. Here using Z contrast image we can see better, so we can this is incoherently image here, and so we can see also some layering here, and the space between the layers around 1.7 nanometers. So here you can say, okay, oh, I found a new phase, new germanium telluride phase, but this is not true, because here this seems to be this and this B and D, these are two twins. You can see if you consider this structure and then you can consider structure model. Here you can see the two twins. So here, just to see, here you have octahedron like pointing here, and here this is an octahedron pointing here. So this is here one line of atoms, and here this is one. So they're sitting like at this angle. But if you allow these two twins just overlap or superimpose, you see that you find like positions here with distances 1.7 nanometer, And if you apply the simulations here, you find that actually this is overlapping domains because of these two twins. So this is not new structure. If you observe it in your samples, so just point to this publication. And so this is like twins which are overlapped one to each other. Now also to the very famous phase change materials, antimony 2 toluene free, but it's not too famous in the phase change community. It's also famous in the community of people who are doing the thermoelectrics or who are preparing spintronics. So this is the structure. Also in this system, the first structure discovered in this system, it's again stable trigonal structure, SGST225. It's also layered structure, crystallizing in the trigonal system here. And it consists of building units, such as building blocks, consisting of 3 tellurium layers. So they form one called quantiples layers here. Also the main structural motif, this is octahedral here, and in between this is like van der Waals like steps. But in this system, this is stable trigonal phase. In this antimony tolerized system, in the case of thin films, there are also reports on the formation of layered and non-layered structure. So non-layered structure, this is similar to the cubic GST225, and layered structure, this is also similar to the vacancy ordered GST225 system. So there are also another phases in this system, also SBT phases like SB2 tellurium free, SB8 tellurium free, SB4 tellurium free. This also maybe interesting phases can be also applied for phase change. Why they are so interesting? Because if you look along a direction, you can see the formation of building units like SBT and the formation of the antimony. This is pure antimony here, like in this phase and in this phase. So intrinsically it forms like domains of SBT and antimony. Here also the same. This difference is only in the layers per unit. There are only few research on phase change properties of this system and also on the growth of such thin films. So now let me look to how to produce these thin films. Again, you can produce these thin films by applying, for example, PLD or another magnetrons pattern or EB. This phase is also, this material, this BT, is also growing at relatively low temperature, starting at 170 centigrade here. This phase you can obtain with very high quality. Here you see some low oscillations here. And if you do rocket curve measurements, it shows you how many grains are tilted in your sample. You can find that this full fit by the half maxima is around on an average 0.04 degree. And for substrate, if you measure substrate, it's also a little bit lower, but it's on this average. This thin film is also growing because it's represent layered structure. It's growing also like with van der Waals, quasi-van der Waals epitaxy. So first tellurium-rich layer is formed here, a self-defined process. And if you do AFM measurements, you see nice domains like here. Steps along the thin films. It shows you also very high quality and also very, very low roughness. It's like 0.2 nanometers. And it's also showing you spiral growth of this antimony telluride thin films. So in retail, you can also, if you use PLD, you can also achieve very high deposition rates, like we used 4 nanometers per minute for growing. You can also achieve 100 nanometers, 100 nanometer per minute for growing of GST or antimony telluride, but the quality will be not so nice. Here, in this case of antimony telluride, they did not find this blackout effect. So after 60 seconds, we see the formation of sticky pattern, which is signature of crystallization of antimony telluride. You can also grow these thin films at room temperature. This we did it recently. And interestingly, you think if you grow your thin films at room temperature, you can produce amorphous thin films. But in the case of antimony telluride, it's not. So if you produce antimony telluride at room temperature, it doesn't matter on each substrate, germanium telluride or silicon or glass, we always form like polycrystalline thin films consisting of crystalline domains and amorphous domains. So these thin films, antimony tellurides, they crystallize even at low temperature, so at very low temperature. Now to the some defects in this system. So one defect which have already discussed, this is the bilayer defects which forms in this system. But in this system we found the formation of periodical these bilayer defects, like you can see here. So it's not like a change of the step between the building units. Now this is like the change of the heights of the units here. And they form because silicon 111 we use unreconstructed surface, so just after etching, and so this surface it has steps, like atomic steps here. And here we can see that some units here starts to form the low number of layers. This is 2 tellurium layers, this is 3, and here intrinsically we introduce this bilayer defects. But this is already defects. And if we combine it with the spiral growth of these materials, we can conclude that these bilayer defects, in this case, this is the dislocation. Because it's a very famous effect, spiral growth. It starts from the dislocations, and this is the screw dislocations. It grows from the substrate to the top of the film. Here you see the screw dislocations like here. Nice. Also, we found also the formation of different twins here, like in-plane twins, 60-degree twins, and 100-degree twins. So this is the common defects in this system. Now to the antimony, to this system. So antimony, this is also one very famous phase change material. Why it's famous, maybe you have some idea. Because it contains only one sort of atoms. It's so if you make phase change, you have no chemical, some domains with different composition. So this is a single phase phase change material. It's also crystallizing in this trigonal space group 166. Structure type also A7 is antimony, as germanium telluride, and density. So if you look also along the A-axis, you can see also some maybe it's layered structure also like antimony, and maybe some spaces in between here. Also, one problem with this antimony is also it has very low crystallization temperature. So if you look here, and you deposit at the room temperature, you see that it has already a low resistive state here, and it does not change on the heating. So if you deposit it like thin films, the thickness of 200 nanometer, it's already crystalline. If you reduce the thickness of this film, you can stabilize the amorphous structure of these materials. You have to reduce it till to 5, 3 or 4 nanometer. Then you can stabilize this phase for a while, but then it's spontaneously crystallizing again to the crystalline structure. So how to deal with this problem? Of course, in this case, you need to somehow to avoid this antimony with different materials. Like if you introduce some selenium here, 1.7% into the antimony, you can stabilize the amorphous phase. Also, you can find, but the transition temperature a little bit even lower than for GST. If you introduce more selenium in this composite, in this antimony, then you can also stabilize these materials, and the crystallization temperature is now like a little bit larger as for GST. It's like at 200 centigrade. So now let me look to the AST material, so-called AST. So this is optical material, also can be used for electrical switches. So this material has only one phase, and it's crystallizing in this phase group 166, crystal system trigonal. And the interesting in this system that same lattice size for all type of atoms. So silver antimony, indium antimony telluride, they occupy the same size. This is also disordered, so this is disordered structure, but it has no vacancies. If you look to the A from A direction, then they see there is no vacancy layers, and also there are no vacancies on the side. Here also some structural investigations. It shows random distribution of all atoms in this structure, but there is phase separation, so there is a domain formation. For example, formation of antimony in this phase. So on the average, it has this composition, but it forms some antimony-rich domains. So now let me conclude this lecture on local structure of phase change materials. So in amorphous state, we have main structural motif, which are defective octahedral configurations, but with one field of tetrahedron for GST225 and germanium telluride. AST, this is this distorted 3+3 octahedron. We found also some voids in this amorphous state, and also we found the formation of the theory. We found the formation of ABAB rings with fourfold ABAB rings for GST with 80% and germanium telluride 86, antimony telluride 81%, but for AST it's a really broad distribution. And the coordination number for germanium antimony telluride, it's germanium antimony GST, it's like 4 for germanium antimony, and tellurium it's 3. For AST it's 3 plus 3. So in the crystalline state, the main structural motif, this is distorted octahedral configurations. As you see here, this is defective, this is distorted. So there are some similarities between crystalline and amorphous state. As I said, it plays a role in the phase changes. We will consider it. So here we have a presence of vacancies for all structures on this tile line, germanium telluride, antimony telluride, but there are no vacancies in AST. And here, of course, we have, like, if we compare with, to use the same terminology for amorphous state, we have like ordered ABAB squares for GST, germanium telluride, and SBT. And here the coordination number, because of ordered structure, it's 6. For GT is 3 plus 2. For AST, 3 plus 3. So at the end, I have some similarities between the structures. This is 4-fold AB units. These are main building units of amorphous and crystalline structures. And these units can be regarded as crystalline seeds in the amorphous space. As I said, we will consider how they play a role in the phase changes. So I think I will stop at this point, because it has no sense to start with another lecture on the bonding, which is a very interesting topic in phase change community. And so we can use this 5 minutes or more for discussion round.
Sir, good afternoon. Sir, I have a doubt regarding in AIST we saw that SP antimony is segregating by itself. So is it possible that we can confirm during from an XRD diffraction or X-ray diffraction pattern that SB is getting segregated like that?
Or if there is enough material, I think yes, you can see some precipitates in the structure.
Okay. For my sample, I am getting tellurium segregated kind of thing. So tellurium.
Yeah, it's also it depends on the composition. As you can see here, I don't know what was your composition, but it's a little bit different. But they found this segregation of antimony. In your case, it can be tellurium. Did you use also AST?
No. GED with arsenic. Tin.
Tin. Okay. Yeah, it's different system and a different crystallization kinetic. So it can bring you to the formation of tellurium precipitates. For example, in the system of germanium selenide or antimony selenide, you have also precipitation of antimony. It's an unstable system. It's decomposed into structures, into two domains like germanium selenide or antimony selenide and antimony. It's material properties.
More questions? Just I have seen when you have used this seed layer and then you have grown that GET and then you have shown some crystallization change. So can you put some more light on that, how it affects actually? If we are growing any film without the layer and with that layer, with this one.
Yeah, I think the formation mechanism here could be that the antimony telluride and germanium telluride they have some similarities in the crystal structure, and so it can nucleate much faster, as in the case of silicon. Here you have a misfit like 10%, so you have to overcome somehow here shown in the reed and to form this structure. Here, because of similarity, I think also the bonding of antimony telluride and germanium telluride, it's like metavalent bonded. This phase can nucleate much faster on this surface.
You also talk about this SB2T3 when we grow. So this is already, it is in a crystalline phase.
Exactly.
So, I mean, it will be thickness dependent, or if the thickness is more, or we are depositing for more time, then only we can see, or if we will reduce the thickness, then we can see some amorphous, or it is always in the crystalline phase when we are depositing.
Yeah, if you use room temperature growth, we did some thin film go in this direction. It remains always amorphous crystalline. So it's like I call it polycrystalline with some domains. Here in this publication we showed that we can reduce this is like 5 nanometers, we can reduce it up to 3 nanometers, but we find still some crystalline domains, crystalline and amorphous. So in our case we cannot stabilize amorphous phase. There are also some reports that during by laser well mentioned, if you go from crystalline to amorphous phase by melt quenching, you can stabilize this phase, but only for several days. Then it goes back to the crystalline.
Because with the sputtering, exactly I'm not sure about that, but we had some deposition and then we have done this kind of this resistivity measurement, and then we have seen a transition which could be identified. So maybe it is already from polycrystalline to some other crystalline phase. It may be that we need to figure out. I need to actually with your work I can figure out this.
We also ask some cooperation partners to grow these thin films by magnetron, because maybe PLD, this is the issue, high energy particles and whatever. But they grew for us also thin films on amorphous substrate, and it was also like polycrystalline thin films. So from some reports they showed that they claim we obtain amorphous phase, and they show X-ray diffraction. But such polycrystalline phase you cannot see the real reflections. So they also, if you grew even by like the thickness 20-30 nanometers, it's sometimes you don't see any reflections. And then if you do TM, some crystalline phases. So somebody may claim that we induce structural changes by FIB preparation, by TM preparation, but I'm not believing in this, because we use special preparation technique, and we are sure that we don't induce the crystallization by our preparation. By FIB, for TM, because it's also sensitive. It's very sensitive. We should be careful about this. Because maybe some people maybe can produce this space, amorphous space, but maybe they have a little bit different stoichiometry. Maybe they are a little bit tellurium rich, I can guess, and then you can stabilize the space. But we used SPT 2 target, and that we are sure that it's this composition what we want.
One last question about this antimony which you have seen, monoatomic, where we can see this resistance and temperature. So compared to this other GST and selenium SPB, this material, there is no change. It is almost from room temperature, it is always. So for memory application, how we can see this? Because normally we figure out, okay, there must be some resistance contrast of this material. So what is the main thing behind this material?
Yeah, it was first published by Salinga. He did the research in IBM group on this material, and he showed if you go to the thickness of like 3 nanometers, you can increase the crystallization temperature. So you can still have this phase change, but still this phase was also not so stable. After the time you have a drift, and then it transforms to the. So maybe by reducing the thickness and maybe a little bit topping, you can stabilize the space.
And then we can see the.
Yeah, there are also some other research from China. They show devices based on these materials, but with such thickness, 3 nanometers, 3-4 nanometers.
So So if no further question, then we can wind up this session, and then we'll meet after this break. So we will meet at 3. So try to come at least 10 minutes prior, okay? So that we can start our session quickly and we can wind up. Okay? Thank you. Thank you so much.